So after opening ADS, we have to select a previous workspace or create a new one. So I'm going to select this one. I have already provided some designs here, some schematics. In this case, I'm going to start with this demo schematic, which is empty, and we're going to design a microstrip line. First start with a microstrip line, we have to specify the type of microstrip that we are using, and for that purpose, we are going to select transmission line as microstrip. Then we place this icon on the schematic, which represents the parameters of the substrate. In this case, we're going to change this, going to specify a height of the substrate of 0.762 millimeters, dielectric constant of 3.2, conductivity I'm not going to change, and the loss specified by the tangent of delta, we're going to provide a value of 0.003, which means that there will be some loss of the line with increasing size. And we just apply this, okay, and here we have our substrate specified on the schematic, okay. Now we want to select a transmission line, and in this case we're going to use this MLIN microstrip line. We're going to place it on the schematic. And this is a simple microstrip line, as we see here. And to specify the parameters of the microstrip line, we need to specify the width, and the width determines the characteristic impedance of the line and then the length. And for that purpose, we're going to use a tool which is placed here, which is line calc, and we're going to start it first. Okay, it has started. After the line calc is open, what we're going to do is we are going to select the component, select again line calc, and then send selected component to line calc. Okay, and here we are. By sending the component to line calc, ADS already updated the substrate, which is defined on the schematic, so the parameters are correct, are the ones that I have specified before. And then we have to specify the frequency at which we want to specify the impedance, for example, of the line. And we're going to, for example, in this example, we're going to select 3 GHz, and then we select here an impedance. In our design, we want to design an impedance of 100 ohms. If we select this option here, it will generate the physical line with a specific width and length. So, and the length is associated with the electric length in degrees. Okay, so at this point we are not going to matter much about this. So we're going to select an impedance of 100 ohms, which will specify the width of our line. Okay, so it has already run, I believe. Yeah. And this corresponds to a width of 0.4786 millimeters. Okay. If we want, for example, a length of this line of 5 millimeters, we can select here 5 and then just simply select Analyze, which will do reverse calculations and will calculate the electrical length of this line. After the physical dimensions of the line have been defined, we can go again to Tools, Line Calc, and then select Update Selected Component, and you're going to see that it's going to update the component on the schematic. Okay, so the values have been updated. Now we have a width of this line which corresponds to the length of corresponds to impedance 100 ohm, and this line has a size or a length of 5 millimeters. Okay. Now we want to calculate the impedance when this line is loaded with a resistor of 50 ohm. So we select lumped components. We place a resistor here. I'm going to rotate the resistor. Okay, and so I need now to connect the line to the resistor, and I need to terminate the resistor to ground. And at the input, I want to measure the impedance here at this point, at the input of the line, and also I want to measure the reflection coefficient. And the reflection coefficient, as I mentioned before, can be obtained by measuring the S11, the first coefficients of the matrix S parameters. And so for that purpose, I'm going to select Simulation S parameters. I'm going to place this component here, or this block, which is associated with the specific type of simulation that we're going to do, and the simulation involves the measurement of S parameters. In this case, I'm mostly interested in calculating the S11, and I'm going to terminate the input with a 50 ohm termination, which is equivalent of saying that the circuit before the transmission line is corresponds to a circuit which has a characteristic impedance of 50 ohm, and so all the calculations will be referred to a characteristic impedance of 50 ohm, which is this value here. And I'm just going to connect these two, and again a ground for the termination here. Okay, and so by doing this, I'm already able to measure this S11 at this point, at this port, at terminal 1. But also I also want to measure the input impedance. And so to measure the input impedance, I'm going to type here Z in. Okay, and I'm going to place this component here. And what it does is it will select the value of S11, and from the value of S11 it will calculate the input impedance. Okay, now the S parameters, what I'm going to do is I'm going to calculate reflection coefficient at a single point at a frequency of 3 GHz. Apply. Okay, that's enough. Now with this design, by pressing the simulation parameter here, it will do the simulation. It opens the display window to display the results. In this case, I'm going just to place a table here, and the table will involve the S parameters, the input impedance, and also I'm going to select here S11, and also I'm going to select the absolute value or the magnitude of S11 separately. Okay, and here it is. Here we have the values of the input impedance, which has an input impedance of 70 ohm. Instead of presenting this result, instead of using magnitude and phase, I want to use real and imaginary part. Okay, so there it is, real and imaginary part, and here we have S11, the magnitude and phase. Okay, I could also try to plot this result, but in this case this doesn't make much sense. I'm going to plot S11. I only have 1 point, so I will only have 1 point in the plot, but let's try it. So by selecting S11, I'm selecting dB to plot the result of the S11 in dB. Okay, pressing OK. Oh, so here we have. Yeah, so we have a 1 point here at 3 gigahertz. Okay, it's simple enough. Sorry. We could also try to compare the result of the simulation that you see here by doing a calculation in Matlab. That's what I'm going to show you now. So here we have a program to calculate input impedance of that circuit that we've just seen. I call this a loaded microstrip line. Here at the beginning I defined the velocity of light. This is the load resistance, 50 ohm. This is the impedance of microstrip line, which is 100 ohm. And here we have an impedance, characteristic impedance of the network, which is 50 ohm. Operating frequency 3 GHz. That's the dielectric constant of the substrate. And here I took the values of the physical size of the microstrip line, which has a width, a depth, a height of the substrate of 0.762 millimeters and has a width of 0.4786 millimeters. And these parameters will be used to calculate the effective dielectric constant. So let me show you this slide here. So you see that for a microstrip line, part of the electric field travels within the substrate, but part of it travels outside the substrate, which in general is air. And so the electric field sees a dielectric constant, which will be a constant dielectric constant between the value of the substrate and that of the air, which is 1. And so we need to calculate an effective dielectric constant, which is calculated according to this value. But as you see here, this value depends on the height of the substrate and also on the width of the line. But these physical parameters, we could only obtain these parameters from ADS. And so I picked those from the simulation and I placed them in Matlab, which is what you see here. And then from these values I calculated the effective dielectric constant. I used the length of the line of 5 millimeters. Then I calculated the propagation constant, which is 2 pi over lambda, and lambda is c divided by the square root of the effective dielectric constant times frequency. Okay, and this value will be used to calculate input impedance of the line according to this expression, which is the known expression for the input impedance of a transmission line, which is loaded by this resistance R sub L. And then from this value I calculate the reflection coefficient and the corresponding magnitude. And so if we go here to these values, okay, and if we compare these values obtained from the Matlab and compare those with ADS, which I'm going to show you now, from ADS at a frequency of 3 GHz, we have an input impedance of 50.3 ohms, real part, and 7.2 imaginary part. And if we look at this value here, we see that the values are very close to each other. They match very well. And also the magnitude of the reflection coefficient is 0.0719, and ADS gives me a value of 0.072. So the results are quite good and match well, which they agree with each other, which means that the result must be okay, either the simulation or the calculation here in Matlab. Going back to ADS, the advantage of ADS is that I can easily here change the range for which I want to calculate the S parameters. Now I'm going to use a linear range, starting, for example, from 1 GHz to 4 GHz. I'm going to use 50 points, apply, okay. And now if I do the simulation, you see that I can very quickly obtain the dependence of the parameters with frequency, okay. And so ADS automatically updates the result either in the table and also in the plot, which makes it very convenient. Also, another thing that I wanted to show you is ADS electromagnetic simulation for a length of line of 5 millimeters. Okay, and I'm going to show you how you can do this very easily in ADS. So starting with the schematic here, we can go to layout, generate update layout. So what it does when I select this option, it will pick up the schematic and try to generate the layout. So I press this, select OK, and now I have here the layout. Okay, the resistance here, the resistor here is a resistor that I need to place if I want to fabricate the PCB. In this case, I want to do a simulation, so I'm going to delete this. And also the termination to ground. And I'm going to go to the electromagnetic setup. First, I'm going to specify the substrate. I'm going to specify a new substrate. Create substrate 1 from schematic. And I'm going to import the substrate from the schematic, which is this demo one. Okay, now I have the correct substrate with the correct height. I save it Okay, and now here it is. The substrate is the correct one. Dielectric constant of 3.2, and the width of 0.7, with a height of 0.762 millimeters. Okay. Yes. Going to place the ports. So the left will be port 1, and I'm going to place a port 2 at the right side. And as you see here, port 1 will have an impedance of 50 ohm, and port 2 has an impedance of 50 ohm as well, which is equivalent of being loaded with a 50 ohm resistance, which is what I want. So this is correct. I'm going to select the frequency plan. I'm going to provide a linear range from 1 to 5 gigahertz, 50 points as well. And now everything is ready. I have the substrate, I have placed the ports. I can now just do a simulation. Is doing the simulation, and the result is here. So here I have S11, okay, which is, if we compare it with other result from the simulation from schematic, it looks very close, but it will be relevant to compare both. And so if I select this, so if I now go here, instead of using the demo schematic, if I select the electromagnetic simulation, which is based on the method of moments, MOM, I now have S11. I edit to the result, and here we see a comparison between the two. We see that there's a slightly mismatch between the two, and this simulation, which uses, which basically is a electromagnetic simulation that solves the full Maxwell equations based on the method of moments, gives us a better or more accurate simulation than the schematic. The schematic one is usually much quicker, and so in first approach in general we will use the schematic simulation as a first step, and then when we want to tune our circuit better, then we will do electromagnetic simulation. Okay, now we have the complete line as required. So you see that very quickly we can do a simulation of electromagnetic simulation of all the S parameters. In this case, we have 4 parameters here, which is the result here. Okay, and now our problem today is to assume that we have a 50 ohm microstrip line, which is loaded with an impedance. The line and the load are not matched, and want to use a quarter wavelength to match this line to the load. Okay. So we know already that the impedance of a quarter wave line must have an impedance which is given by the geometric mean between the load and the characteristic impedance of the line. And the electrical length of the line is 90 degrees, which means that in line calc the electric length must be set to 90 degrees when designing the line. And now my final question is, what result should we obtain in ADS to check that the line is indeed matched? What parameter gives us the information that the result is the right one, the one is we want? Something I leave you to answer. And let's move to ADS.